hear you. Hang on. What's going on? I can't hear you. Oh, I think it's at your end. I'll check my settings. Hey, Pam. Can you hear me, Pam?
Yes, I can.
And I can hear you. So, Rose, say something. No. So, how are you, sir?
I'm all right. How are you?
Very, very good. It's been a really interesting week. Oh.
Trying again.
I'll try again. No, I was really blown away by the neural Turing machine paper. It's remarkable work. Really, really amazing. I looked at the citations. Nothing particularly, maybe I didn't go far enough down the list. It has like 1,300 or something citations, but I looked at the ones that were cited after it. And
so what is it promised to do? I don't know anything about
well,
neural.
we'll see if Rose and Rob join in and I'll give you a quick surmise. But yeah, basically it's replicating the known machines and Turing machines sort of in a continuous variable variant. So, okay, and unmute and we'll try again.
Any difference?
Oh yes, massive difference.
Oh,
How are you?
no, I can't hear you.
You can choose one or the other.
How have you been? How's things?
I don't think she can hear us.
Oh no. Yeah, so basically I've gone back and I'm just learning again. I clearly found a big gap in my understanding. And so I've been hitting the books and just learning all week, trying to fill in the gaps. But,
Cool.
yeah.
Yeah, I see this neural Turing machine was a pretty popular paper.
Yeah. And there's Rob.
Hey, Rob.
Oh, drink delivery service, very nice. You're muted still, Rob. Oh, hang on, sorry, there's somebody at the door. I don't know who that is. We can't hear you, Rob, because you're muted. Can you hear us, Rose? No.
Can you guys hear me?
Yes.
I can't hear you.
Okay, should we talk then so you can hear us?
Testing, testing.
Yeah, it sounds like she can choose whether to speak or to be to hear us.
Oh,
so,
I hear you. I hear
Okay,
you.
good, good.
Well done.
That was so weird. Sorry.
So, welcome back. How have you been?
Good to see you.
I've been okay. It's been a sort of a rough month. My father passed away.
Oh man.
Sorry for your loss.
It's just always difficult being out of the country, right? But
My mum passed a few years ago and I was stuck here with COVID, so.
oh yeah, no, I did get to go back. But yeah, it's hard being away now. Like I'd like to be closer to my mother, but
Yeah. Yeah, I'm heading over to Australia in 2 weeks to spend some time with my dad, who's 94, so. Yeah.
oh, that's a good age.
Yeah, so yeah, similar idea, just get to see everyone. I mean, he's reasonably okay, but at that age, it's very hard to kind of make it.
Yeah, I don't think you'll regret these trips. I had gone in July and I had spent time with him and I was really glad that I had.
Good,
Yeah.
very good.
So where is home, Rose?
Yeah, I was there yesterday.
Like where is my family?
Yeah.
In Ireland, west coast of Ireland, in Kerry.
Nice. Okay, so Piam's kind of got the shtick this week. He gave us this wonderful article by David Deutsch from 2014, I think it is. Did you have a chance to see it all, Rose?
I haven't, so I'll just be quiet and listen.
No, that's fine.
Yeah, I mean,
Yeah,
looked
we
at the
don't
other
have
stuff.
to talk about it. we can
Oh,
talk
okay,
about
well, we
anything
can try
else.
again next time if you like. I think it's a very relevant and interesting article, or we can cover some other material that's.
Go ahead and I'll just listen and I can catch up by reading it afterwards.
Yeah, sorry. I went through, there was a paper and a couple videos. That was
That's
from
right.
Massachusetts. I went
That's
through
the
that
other
stuff.
possibility, yeah.
Um,
So I'd like to give you a brief summary of neural Turing machines and specifically one concept from them, which I thought was really amazing. So the neural Turing machines paper, and I'll see if I can dig it up here. Where is it? Anyway, you can just literally Google neural Turing machines and it'll pop up as the top thing. It's a 2022 paper, I think. It's very recent, the last couple of years. So what they did was they
First one was 2014, right?
neural Turing machines?
Yeah.
2014. Okay, yes, so it's been around for a while. So I've been looking at attention and multiple attention heads rows. So let me give you a brief summary. So the idea of multiple attention heads, and I'll bring up my Rhino picture because I think that actually helps. So let's pick this up. Start here.
Well, I do have a question for you when you get into that.
Yep. Go ahead. I'm just trying to explain it to Rose so that she can follow along. Okay, so I'll just jump in if I may. Share screen, this one. All right, so here we have a classic autoencoder or GAN. Okay, so basically you have some high dimensional input. It goes through a series of layers and then it ends up as some latent representation in the middle, which is compressed. I have some ideas about the benefit of this. And then that latent representation is then essentially expanded back out into a high dimensional output. All right. And the GAN, both the GAN and the autoencoder work on the principle of, sorry, there's somebody at our door. That's very strange. Sorry, one sec. Somebody here. Anyway, sorry, very distracting. Okay, so we have this basically this high dimensional down to a low dimensional back to a high dimensional. And when we train the model, there are the memory of the past is encoded in the weights in the layers. Essentially, past experience is encoded into these blocks here and here. And the latent space itself can only be interpreted by these layers and can only be generated by these layers. Okay. So that's the classic autoencoder GAN style model. Any questions at this point or any clarifications I could offer? Goodness, it's very noisy.
Yeah.
Today.
So I got one. Could you look at the latent space as essentially an economic model?
Pause that.
In other words, you're taking all this information, you're trying to distill it into some sort of really parsimonious representation.
Yes. Yes. Yes, you could, is my, yes. So, sorry, I'm just trying to. So parsimonious, yeah. So basically, to use the language from the David Deutsch paper that we'll be looking at next time, you can generate explanations from the from the latent representation that have few enough variables that we can actually understand what it is that they represent, if that helps. So creating representations that are low dimensional, in my opinion, is equivalent to coming up with explanations.
Yeah, so that, you know, that little pink square would summarize social science, for example.
Yes.
I don't know, I guess, what you mean by that. I mean, it's a bunch of numbers, right? If to the extent that you think a bunch of numbers in a vector can explain everything, then yes. But I think all it does is that if there are two things in, so I think the easiest version of latent space I've seen, like the most intuitive, is like the word2vec. So when you train it, like if you put two words that have some similarity through the network, they end up being close together in the latent space. That's all it does. Like if you put cat and dog, they go close together. Flower and dog would be farther apart, but flower would be closer to tree. So that you get some concept of similarity between concepts. That's it. I don't think it can cover the entire economics theory in a bunch of numbers.
Okay, let me toss out a different perspective. So in economics, we've got something we call a Cobb-Douglas production function. And it's really kind of abstract, and what it says is that we have labor as an input, and then we have capital, which is kind of ill-defined as an input, and that explains output. So in that sense, what you do is look at GDP and say, okay, we can reduce that to a particular parameterization of these two factors. Now, I'm not saying that's good or that's not good, but this is sort of how a lot of social science type models function. I mean, there's some tangible thing that they're trying to represent, but there's a bunch of stuff going on, so they try and distill it down into some, you know, operational set of factors.
Yeah, but I mean, it's basically a function, right? You put in some inputs and it
This is
gives you what you
function.
want, right? I mean, so yeah, so it could be but again, the problem I think with like using neural networks for approximating function is you need to have the answers a billion times over, then it learns what that function is. I don't think there is, so so I guess you could do what David is proposing here, like some kind of an autoencoder where, let's say you don't know the answers, you just want to be able to reproduce all the data and then hope that that latent space contains something that you want. But I think extracting it out of the latent space is then the problem you want to solve.
Yes, correct. I would agree that extracting the explanation from the latent space is what you want. I agree completely. Yes. So the latent space itself is not an explanation. It's just in fact, it's just a bunch of numbers, exactly as you say, Pine. Like the latent vector is just a bunch of numbers, and it only has meaning in terms of the decoder. The decoder is the only mechanism that can actually take that bunch of numbers, that latent representation, and generate something that we could perceive and understand. I completely agree. So fair comment, Pine. I'm not saying that your comments are incorrect, but let's try and answer your question in a slightly more complicated way. So, sorry, this is just such a terrible diagram. I need to really sort this out. Sorry, I have to edit it every time I want to show a picture. So what I'm trying to get at here is the following, is that, so there's one regime where you have one encoder and one decoder, and then you train them on some data, okay? So what happens there is that the encoder gets really good at taking a high dimensional input and representing it as a consistent and coherent low dimensional representation. That's the latent vector. And then the decoder can take that latent vector and generate a high dimensional representation that's very similar to the input. Okay. You do that a billion times. It's unsupervised learning, which is the magic trick that's so interesting here. You do that a billion times and the encoder and the decoder get really good. Okay, so that's step one. let's say. Step 2 is I now hold the decoder constant. In other words, I no longer backprop through the output, through the decoder, and it's held constant. And now, because it's being held constant, it becomes what's called in the literature a generator. So the generator basically can increase the dimensionality or transform the latent vector into a different kind of representation according to its priors, okay, and its structure. So what we can now do, and this is the magic trick, is we can now hold that constant and then train different encoders which have different reward functions or different loss functions or different values or different preferences, if you like. Okay, and the point here is that they all have to target the same latent representation. In other words, now what we have is we have a bunch of different encoders that can encode to a common decoder. Okay, so they could have different concerns. So in the case of DALI, and well, let's not use DALI, let's just use AGAN. In the case of AGAN, you could have different encoders that could take, like one might take a picture and then you get a picture as the output, one might take some text and then you get a picture as the output, one might take body gestures and encode those into a picture and so on. So we could create a large diversity of encoders in a completely unsupervised training manner, right? So now like there's no markup, nothing. And we can now, now we've got this reusable decoder and this collection of encoders. Okay, so we have a bunch of evidence, and this is the economics encoder. Okay, and this is the biology encoder, and this is the medicine or something other encoder. And they can essentially generate these latent representations that will project through here. So different explanations, if you will, all right, generate, we could consider these as different explanations or different attention heads. Okay, so this is where we get into neural Turing machines, which is really interesting. So,
okay, but the latent space is going to be different for each of the,
no, it's the same.
The green pyramids.
It's the same. They all are targeting the same latent representation. So imagine that I give you a control panel with knobs and dials and switches on it. None of them are labeled, okay? And there's a robot arm over there, okay? And there's some wiring between these knobs and dials and switches that controls that robot. And you don't know what that is yet. So what you can do is you can fiddle, right? You can just iteratively, randomly try stuff and build associations and work out how to control the robot. And if you do that for 1,000 years, guess what? You'll get really good at controlling the robot. Okay, and now there's this other interface where it just has a camera that's looking at you, and there's a robot over there, and if you wave, the robot goes up, and if you wave with your left hand, it goes left, and so you start doing this, and now you're controlling the robot, not with knobs and dials, with gestures. Okay, and now you're doing it with voice. Oh, okay, I want you to pick up the apple. Okay, that didn't work. I'll move left, move left, move left. Okay, go down, go down, go down. Close your jaw, lift up, lift up. So we can create different ways of encoding the information into a way that the robot we can control the robot in a predictable way, but learning to control the robot in an unsupervised manner. Okay. So
David, can I interrupt for a second just to make sure I'm understanding?
Yeah.
So the latent space at some point has to be linked to some sort of outcome or representation that you're looking for.
Okay, so step one, we trained again, just in the normal way.
Train the GAN to do what though? Like use your robot.
Match the input to the output. I show you, I have a robot that picks up an apple over here, and you have to get, and they, and then it works out, oh, okay, I'm picking up the apple now, all right? So the input equals the output. So we train the robot in a completely unsupervised manner.
The picks up the apple is what the latent space is sort of is coupled with picks up
it's
the apple.
coupled with the actuators on the robot arm, right? So the output of the brown box there is the control signals to the robot, right? The voltage levels of all the different motors and the settings and all that other stuff, right? It's got a high dimensional representation that is used to control it. We've squished that down into a latent vector, and then we've trained a bunch of different ways of generating robotic control through that latent vector, if that makes any sense. Another way of thinking about it.
I guess what I'm asking is that latent space tightly coupled to pick up the apple, or is it more general? Is it more generalized?
Okay, here's another way of thinking about it that's a bit more contentious. So your body is the thing on the right. Okay, so it is, and the latent vector is your spinal cord, let's say, all right? And we have all these different attention heads in your brain, and one attention head takes over and makes a cup of coffee, and then another attention head takes over and you walk down the street. And another attention head comes along and you start juggling, okay? So there's only one body and there's only one kind of way you can control it, which is the way that it's learnt how to interpret signals from the nervous system or the whichever system. And what we can do is we can have many different little brains, if you like, or little attention heads that can take over. All right, so now we're not thinking of the brain as a monolithic lump, we're thinking of it as a bunch of little brains. And these little brains basically are using different, one of them will take over and allow you to perform some task, right? Balancing on a tightrope or riding a bicycle or driving a car or something, right? So we have some set of memories that are contextually specific, some finite game that we played called driving the car. And then that generates a latent representation, which is then picked up by the body and you end up controlling the vehicle, right? So that's the kind of idea behind the multiple attention heads, as I understand it in my current reading, which is poor, and I'm trying to fix this, but I'm just trying to give you a sense of where I'm going with this idea. So in the economics model, you'll have a buyer and a seller, okay? So this guy here, because of his preferences and because of his priors, he wants to buy, okay? And because this guy here, because of his preferences and his priors, he wants to sell, okay? But there's only one mechanic, there's only one mechanism to actually do that, right? You go to the stock market and you put in a bid, and then somebody accepts it, and there's a bunch of machinery, if you will. Okay, so you can also think of these as agents, separate agents, people, if you like, or cultures, if you like, all right? And there's only one world, if you like. So we have to interact through the world through this tiny little latent vector, and then that will basically generate outcomes, and we all use the same world. We all come to the world through the same door, if you will. And that is the big idea for multiple encoders. Any questions or comments, or does that make any sense, or is that too weird? I don't know.
No, I mean, I find it very interesting. I mean, there's a lot in sort of, behavioral economics, behavioral finance that would lend itself to this type of perspective.
Yes, I believe so too.
But part of the challenge there is figuring out which attention head you're going to pay attention to.
Right.
Or, and maybe it's not, a 0, 1.
No, that is exactly the correct question. That is perfect, yes. And that is exactly what neural Turing machines attempt to answer, which is which attention head should we use? And that's fascinating. And their answer is equally fascinating. And I invite you to read the paper if you're interested. I can give you a summary now, or I would prefer if you come up with your own conclusion, but if you like, I can kind of summarize. So I'll give you a brief summary. So what they come up with is 2 addressing schemes, okay? One addressing scheme is what they call content-based addressing. Okay, so what do I mean by addressing? Okay, so I think I'll just try and explain it and then we'll pick up the pieces because I'm not going to do a good job. So content-based addressing means that, have I seen this before, right? So if I see a bicycle or if I see a dog running towards me, okay, I'm going to use that content to select which attention head is dominant, right? I'm going to run away, or I'm going to go into a defensive posture or something, right? So there's this idea of the content of our of the high dimensional space actually directly switching to the correct attention head. All right, so that's what's called content-based addressing. And then there's what they call position-based addressing, which I would call relative position-based. So in the relative mode, what happens is that you stay within the attention head, but it changes its state a little. Okay, the arm has moved, the arm has moved, the arm has moved, the arm has moved. Now I can start opening my hand. So there's this fundamental difference between staying in. So if you're inside the finite game and the rules haven't been broken, then you're in this kind of relative addressing scheme where you're not going to move very far in the latent space because the current attention head is, has a plan and is controlling the situation and is trying to get some outcome, right? I'm walking to the shop to buy some milk. Okay, so that attention head is running the show, and then this dog starts running towards me, and the content-based addressing system kicks in, and that actually triggers a switch between the attention heads, right? So this gets into cognitive science and other stuff. There's this system in your, there's 5 kinds of attention in the human brain at least, according to McGilchrist, as I recall. And one of them he calls the vigilance system. So the interesting thing about attention heads, and this is the subtle point which I really don't see much in the literature, is that they are constantly attending. Okay, they are always on all the time. They're usually very quiet, like they're not having a problem, but they're certainly engaged. They're not turned off, they're not dead, right? They're fully active, but they're content, they haven't been switched on, if you will, in the sense that they're not dominant in the attention motif. So all the different attention heads have a set of priors, and if they see content in the environment that triggers the vigilance system. So my understanding, as best as I can read, which I haven't read that much and I need to read more, is that the vigilance system basically says it identifies something, some piece of content, and then it essentially, there's an option. What should we do with this new piece of information, right? And if everyone is quiescent, then the answer is nothing. It's not relevant. Nobody sees a threat here. Nobody sees a problem here. And the vigilance system shuts down. Okay, so if there's novelty in the perceptions, this kind of auction is held, and then if somebody really reacts very strongly to that, they'll be granted control of the decoder, right? So if you know what to do when this dog is running towards you, I'll give you control. And that's what the vigilance system is doing. And if the vigilance system isn't firing, then the current attention head maintains control. That's a kind of a crude version of how the various different attention heads share control of the decoder. Anyway, have a read of the Neural Turing Machines paper and make your own judgments on that. That's my interpretation. Any comments or thoughts at this point?
So I guess maybe one general question, I guess I'm getting confused with like different, so you seem to be like going back and forth between very different levels of abstraction, all the way to like modeling the economy and biology, to then what a person does when loud noise comes in, you're switching between having taking actions versus just the representation which you're showing. You're switching between GANs and autoencoders that are totally different things. So which one, I guess, do you want to focus on for? Because to me, these are like very, very different things. They might be connected at the high level that you're talking about, like behavioral, like brain level, which is valid. But I mean, for example, like the diagram you're showing, so these kind of autoencoders have been usually used for images for obvious reason that the input dimension can be kept constant. But if you want to do this for like tabular data, or let's say biology and economy, they will have different number of features, different structures. You can't put them in a neural network like this. So I guess I would want to know how you would actually do this operationally, but maybe that's not what you care about. Maybe you're thinking about like at a higher level of abstraction, there will be some model that takes it and puts it in a representation. But I've never seen anybody doing this for like random unstructured data. That's, as far as I know, is beyond the state of the art. But have you seen any papers of people doing these things on anything other than images?
GANs?
Well,
yes.
Yeah, GANs, you can do that, but I don't think you can go train a GAN. So first of all, GAN is totally different, right? You're not encoding and decoding images. That's just not what GANs do. You generate an image and you say whether it's real or not. That's it.
But there is a latent vector, and there is an encoder and a decoder.
There is no decoder. It's a discriminator. That it's a binary classifier, right? It's not a decoder. Decoder is when you go from the latent space back to the original image.
I see. So there's no generative component of a GAN? That seems odd.
No, there is a generative component, but there is no decoder. There is then a classifier that tells you whether what you generated is correct or not. Or
I will look deeper into GAN. Once again, I spent the whole week reading literature because my knowledge in this area is so abysmal.
No, but I think what you're describing is like an autoencoder, which I think that makes sense. So you're trying to like generate or go into a latent space and regenerate it. But I think going back to, I think one of the things Rose said, I don't think that latent representation is a universal, unique thing that you can do for all these fields combined and then use it. I think depending on what you want to get out of your latent representation, you would pick different ones. So that's, I think, the main fundamental issue that I have with this, that you can't.
Sure, and it's a valid issue, and fair comment. And I'm really, I thank you for that, and I really want to improve my understanding. So I'll give you another kind of thing that I've been thinking about, which is one of the biggest problem with GANs and autoencoders is that they often don't converge. They don't learn anything, right? They just fall apart. The encoder just says true and it always gets it right, and then the decoder never learns anything, or vice versa. You know, sure, there are problems. So can we, using the same kind of argument I used earlier, not train the decoder and just wire up the control panel to the robot using conventional systems, but still don't label any of the controls? So now it's a deterministic system. And I would argue the decoder is somewhat deterministic as well, but it's not really a neural network. It's just a
sorry.
mechanism.
Before you continue, can you explain again? So now you went again to taking actions. Like none of there's no action in these things, right? You have some input, you reproduce the input. There is nobody taking action. So that's a totally different problem setting. How do you go from? So what are you outputting that would give you an action by a robot or a person?
Excellent question. I'll try and answer it, but I may get that wrong. So the decoder, in my intuition, you specify what you want to see. You imagine what you want to see. I want to see the robot here. And that is, so you could make it like a GAN, okay, or a picture. So I imagine seeing a picture of a robot holding an apple, okay. So that is the output that the system is trying to produce. And the only mechanic, rather than generating pixels, it's just a camera pointed at a real robot. But the problem setting is the same. You have a bunch of parameters that are controlling the content of the image. In this case, we're controlling motors and other things. The GAN is learning to control, or the audio encoder, or whatever you want to call it, is trying to reproduce the input, trying to reproduce the input as the output. And the mechanic.
But the autoencoder, does it have control over like the robot arm? Or like, I don't understand, how do you hook up an autoencoder to a robot?
Put a person there and just say, here's a picture of the robot I want to see. I want to see it holding an apple. And then the guy walks over and just positions the robot so that it's holding the apple, and that's the decoder. Okay. It's
okay.
not, there's no magic here, right? And then I take a photograph of it, I send it to you, and you say, that's not real or that's real. Okay.
Okay.
There's some mechanism that does involve action. I mean, there's action going on in the layers of the network. It's doing computation. It's doing something. It's not just looking at the table. It's multiplying things and adding them together, and even making choices in certain situations. It is a continuous domain, but it is a bunch of actions, I would argue. The autoencoder is not instant. It may have to do a lot of work to produce an output given some input. So there's no specific time constraint on the autoencoder. These are weak arguments. I'm just trying to present a response.
At some point in time, you have to have a question you're trying to answer, and there's an output from that then's picked up by something else, right, to take an action.
Say that again, sorry, I'm trying to pass.
Like, if you look at each of these units, what you have displayed here, this is a unit that's trying to answer or assess one piece of something, right? It's trying to answer one question or one state of something, right? Is this an apple? Is like, it's trying to give a yes or no answer, or a category, danger or not danger, something, right?
It's not trying to give you an assessment, I would argue. It's trying to, so this gets back to the sequence of operations, which gets back to the neural Turing machine. So the neural Turing machine can basically run programs, right? It can run a piece of software, right? So I need to have some milk, okay? So let's construct a program to do that. Okay, I'll walk down to the shop and buy some milk and come home, and then I'll have milk. Okay, that won't happen instantly, but that will produce essentially a time series of landmarks and expectations, right? And then once I get to my first expectation, the program will move on to the next step. And okay, I'm expecting to be walking on the sidewalk heading towards the shop. Am I there? Okay, great. All right, stay in this state for a while. I'm heading towards the shop. I'm going, you know, da, da, da. Okay, all right, state change. I can see the milk, content-based, update, okay, change state, so on. So the idea of the neural Turing machine is that you can create programs. You can create schedules where one thing leads to the next, and you have a kind of very, very fuzzy state machine, if you will, that you can move through. And I'm suggesting that some mechanism like that might be at play. Not sure. This is very, I'm trying to resolve this with philosophy and McGilchrist and a bunch of other things. So Payam's comment is dead on, and then I'm all over the map. Fair comment, and that is a weakness. I completely agree.
No, I'm just trying to understand, like it might make sense. It's just because you switch between different things, I get confused. So,
yeah, so fair comment. Yeah, so my goal is to try, and what I do to test this is I go back and I re-listen to philosophy books with this idea in mind and see if it's contradicted by the great philosophers of history, or whether it's somewhat coherent and consistent with their thinking. And then I, you know, jump around the literature and try and see if there's anything grossly wrong with it. And I haven't detected that yet, but that doesn't mean that I'm not completely off the base here. It just means I haven't found a strong argument to tell me why this is wrong. But there it is.
I guess what I was trying to get at is that these things need to be replicated and maybe replicated across layers of abstraction. And so, like, back to what Payam was saying about, like biology versus social science versus something else. Like at some point you're doing all of these things on a very micro level, and you're getting an output from it that's being monitored by something else and taking 5 other things like, you know, the color, the position, the something else, and determining apple, no apple, or whatever. You're stacking them on top of each other, right? And each of the cells is probably self-contained.
Yeah, I think if you solve what you set out to solve, you basically solve AGI, right? That's basically what you're doing. It's just that I think we're probably very far away from it. So you probably have to pick one corner and start from there, like everybody is.
For sure. Once again, I have to kind of get a distant horizon that we could all move towards, and maybe this is completely the wrong horizon. I don't know, but fair comment. So Rose, and I'll share this with you, I'm actually trying to codify this as a paper. It's very weak at this point, but I'll share what I've done, and I'll literally share the document with you. But there's a piece of the paper that I think I'd like to, so this is not a, this is wrong. This is the auto encoder. Oh, that's the game. Sorry. Anyway, I'll leave that for now. I added a section here. I don't know if you saw it.
Where are you planning to publish this?
Probably on Medium or something. It doesn't really quantify as being academic. I don't know. We'll see. Maybe I can morph it into something that Rob and I could publish under the economics banner. I don't know. Yeah, so you were talking about scale jumping, and I'm completely guilty of that. And the reason is this Lynn Margulis. Have you heard of Lynn Margulis, Rose? Have you encountered her at all?
No.
Oh, okay. She's a very controversial evolutionary biologist, and she basically came up with this idea of endosymbiosis, where I'll let you read the stuff itself. I find it very hard to kind of summarize that easily. She basically, I don't know if you know this about cells, but cells contain cells, right? Your mitochondria's DNA is completely discontinuous, has a completely different genetic history, and has absolutely nothing to do with your quote unquote DNA, which is just the encasing cell, the DNA of the encasing cell. But within that encasing cell, there are many other cells which have a completely different genetic heritage, but they've all kind of glommed together into a society or a culture or whatever you want to call it. And that collection of cells we call a cell, but it's not really a cell, because if you look inside the box, there's cells, and if you look inside the box, there's cells, you know, or they're not cells anymore, but there's some other. So there's this scale independence, right? This idea that these complex systems can embed themselves in other complex systems in a symbiotic manner, and the whole system basically stacks up vertically as well as horizontally. Bad explanation, but
No, that makes complete sense to me.
yeah.
And I think that there was an element of that. I guess I was seeing that in what you were presenting.
Right, right. Yeah, so basically the idea is that there are these attention heads that are quite limited in what they do, right? They're not that complicated. They're actually quite simple, okay? They're typically doing nothing, but that doesn't mean they're turned off or they're dead. They're just, they're not active, right? They're just quiescently sitting there ready to go. Their interactions are often very useful and very beneficial to the host, right? So when they're needed, they're there and they're active and they're available, and you can switch them on and they do something really useful. And occasionally they're destructive, right? Occasionally they do bad things, cancer and other things like that. But typically, at every layer of scale, we have these different attention heads. So that was one kind of key concept that I was trying to get at. And then this is where I kind of fell off the bus here, because I was looking at autoencoders and I was trying to get an understanding of that. I was looking at variational audio encoders. Thank you, Chaim. It's very interesting. I'll learn more about that. And then I was trying to do attention mechanisms, and attention is all you need. And Chaim sent me a course, which I will do, which should help me on that. But I just haven't been able to find a good summary paper on attention. If anyone knows of a good summary paper on attention, I'd love to see that. But I haven't seen it. I'm trying to gain a deeper understanding, but my goal here is to try and list out GANs and neural Turing machines and other mechanics at this point. And then there's some very early work, but this is very, very early. But I'm just trying to give you a sense of what the point of all of this is I'm trying to put together a paper of some description that describes this idea so it could be used by others in general. And I would really appreciate any help on this that you might offer.
By the way, David, I came across this one. I was going to send it earlier. So you were talking about you wanted to interpolate in the latent space.
Yes.
So this is like a code developed by, I think, Francois Cholet. He wrote this code to interpolate in the latent space of a stable diffusion model.
Oh, wow.
So it's really cool. Like, you check out some of the things they did. Like, it's a random walk, but I guess you want to make it guided in a way. So I think that's exactly what you were trying to do.
Yeah, very good. No, I've been playing with stable diffusion, getting some absolutely stellar results out of it. It's just, have you played with stable diffusion yet, Rose? Do you have a GPU at home?
I had, except I'm in a BitLocker hell at the moment.
Oh, okay.
And I think the GPU caused it, actually.
So have you seen the output of anyway, that's off topic, but yeah. So I'm working with another couple of guys on trying to fly through latent space in virtual reality, but that work is ongoing and really hasn't gotten very far yet, but we're getting there. We're slowly coming along. Goodness, I've been all over the map today and I've been doing all the talking, so I apologize for that. So let's go and let's think about Rob's financial data. So Rob has some really interesting financial data, and it's basically different attention heads or different. So the underlying data stream, as I understand it, is equivalent for all the different metrics of liquidity, right? So we have an underlying data source that is consistent across all the various different agents that are looking at it. The agents come up with different assessments, and so we have, 250 plus stocks across 250 days of trading or something like that. And we have 200 or so different observers of that. Of those stocks across that time period. So we really do have something quite similar to what I was trying to show you earlier, in my conception at least. And what would be interesting, I think, would be to try and use those different perspectives to essentially reconstitute the underlying data. Perhaps that might be a very interesting way of thinking about it, because if we could use those different interpretations to reconstruct the underlying data, then we could make predictions in those representations and generate future data, if that makes sense. So we could extrapolate across the different metrics. And so what I'm suggesting is we use the various different inputs to train a generator that generates the stock price. So given these, or all the stock prices, if you like. So given these metrics across this time series, can you tell me what the stock price is at this point in time, let's say. And if we can do that, then we might be able to extrapolate on these metrics and then generate counterfactual predictions of the stock market by using many different attention heads that have different concerns and different preferences. We should be able to reconstruct the underlying data. So that's one way we could approach Rob's problem. Any comments?
I guess if you can do that, you become very rich, right? Like if you can generate future stock data, you don't even need attention heads.
No, you
go
can't,
bid on
because the stock market is not it doesn't fulfill Bayes' theory, right? Your priors only help you to a point, right? So the past is not an accurate, it's pretty good at predicting the future, but by no means can it actually do that, because of chaos theory and all that, small differences, having big changes, all this other stuff. So you can't accurately predict the stock market, but you might be able to statistically guess better likelihoods of the future than others, perhaps. I think that's possible in a general approach. Rob, any comments on it? Does that make sense?
You're
muted. Muted.
Yeah, that would fall under the prediction heading, I would argue. So, I mean, you know, at some level, trading is kind of like a coin flip.
Yes.
But if you could figure out that, you know, 1 out of 5 times, it's not a coin flip, and in those circumstances, come up with a better prediction, then yeah, you could use that to make a lot.
Yeah, I think that's plausible. But you could also improve medical predictions, for example, right? So we could take many different diagnoses made by different doctors and potentially use that to essentially train a model to try and estimate the underlying condition, or at least the distribution, the probability distribution of the underlying condition, which would cause these different observers or different attention heads to make their various different assessments.
You know, another area too is, you know, if you can simply characterize what those data distributions will look like, that's actually very valuable. So I don't know, you're a company, you're starting a new marketing campaign. Can you characterize sort of what the range of outcomes might be?
Counterfactual analysis, yeah.
So, I mean, if you could do that, and that perhaps that range of output or range of possibilities includes a bunch of really negative scenarios, you think, okay, maybe we don't want to do this. You know, so we got a, you know, like a 1 out of 4 chance of blowing up the company if we do this. Maybe we'll back off.
Yeah, but maybe 1 in 4 is the best odds you've got. So,
possible, yep.
So that has to be taken under consideration. Yeah, so there's some absolutely amazing papers from SIGGRAPH this year which cover this. Unfortunately, it's behind a paywall, but I'll try and find some content that is openly available and share it with you. But there were some truly remarkable machine learning applications in SIGGRAPH this year, and I haven't even gotten to. Have you looked at the stuff from? What's the other one from Europe's? The other conference, not Europe's, but NIP. No, what's the other?
ICLR.
ICLR. That's the one that happened quite recently, right?
Yeah.
Have you looked at the papers at all?
Not yet. There is so many that I look at it, I'm overwhelmed. I don't even get started because there's like so many interesting workshops and papers. So.
I mean, I went to SIGGRAPH 2 months ago and I'm still watching videos of presentations because they're just crazy. Anyway, there's some highly relevant and coherent stuff from SIGGRAPH that's very close to what I'm talking about, actually. So I'll try and help you get
But
access to
isn't
that.
SIGGRAPH stuff all about like machine vision and graphics? How is that related to financial?
So a lot of it's about human perception. So in virtual reality, what they're doing is they've how do I put this? I'll try and give you a brief summary. So visual cognition has multiple attention heads. Okay, so I can, I'll give you an example. So if I walk into a room that's dimly lit, okay, and I can just see some landmarks, I can see some tables and some chairs and so on. And I'm trying to navigate through that room. The attention head that's navigating me through the room actually won't be affected if I turn the light on, unless something surprising pops up that I hadn't seen when the light was off. So basically, these different attention heads need to be characterized independently. So we have one attention head that's managing navigation. There's another one that's managing something called vection. It's a different idea. But basically, the neuroscience and the cognitive science in virtual reality is highly coupled to this idea and is becoming more and more, coming more and more closer to this idea of these concurrent attention heads having to be managed somewhat separately, right? So you have to maintain this in order to keep this going, but you can change that. So I can have a conversation with you while I'm walking, and I can also be holding a shopping bag or even manipulating something while I'm talking to you. I can be using my phone and walking and so on. It gets harder and harder, but we can actually have multiple attention heads simultaneously acting. And that's a lot of that kind of shows up in the work at SIGGRAPH. That's kind of the link.
Okay, cool. There's another one you might be interested about, which is related to what you said. There's this concept called option keyboard. It's a famous paper that came out. It's in reinforcement learning, but it's about exactly what you said. Like you have to do a bunch of skills, and each one of them is, let me just share I haven't read this paper, but
I'd love to. Thank you.
If you care about like actions in the reinforcement learning segment, that's basically what it is, option keyboard. So they train this spider to basically, the keyboard is like a keyboard as in a musical keyboard. And it's basically, it's an analogy to playing different notes at the same time. And those notes would mean either walking or talking or something else. And how do you play them at the same time?
Right, but this adds credibility to the idea of the multiple attention heads controlling one system, if you will. Right? So that's where that idea emerges from. It's not my idea; it comes from others, but that's the general idea. And then when we look at Rob's data, we have a very similar situation where we have all these different ways, these different preferences for measuring liquidity. Those different preferences represent different kind of essentially encoders. They encode the same information in slightly different ways. And can we use those encodings to essentially reconstruct the input? And if we could, then we could essentially manipulate the latent space, which is the actual, the spreadsheet. And we should be able to generate predictions. And I think we could also do that in medicine if we had a data set. Do you have a data set, Rose, that we could try this on? Is there a situation where you have a bunch of patients who have had diagnoses done by more than one doctor? And could we take that information and try and encode it in some way so that we could try and basically build a statistical model of the underlying condition? Does that make sense?
Yeah, I actually have sort of given up hope that any of this is ever going to work on a medical data set.
Okay, fair enough.
I had done a bunch of stuff with attention and ICU data sets probably 2 years ago now.
Okay.
And what the model focused on it was never objective data. It was never physical facts.
No, you don't. Yeah, I understand that there were some representation of physical facts, right? So there were some underlying physical facts.
No, it basically focused on a progression. Like these are the drugs that people will end up taking when they're already sick. There was no way to build causal stories where you could intervene upon it.
Yeah.
It was really disheartening. And I guess listening to the conversation here, what I'm thinking is that the stock market is probably the best application you can get, because it really is about narrative, and you want prediction that you can take advantage of at that moment in time. And then you change the entire picture once you've done that, right? As soon as you exploit, now a whole new set of rules need to come in. You can't keep exploiting in the same way.
No, absolutely not. Correct. Yes, yes. Because
So then your model becomes useless, right? You basically need to then sit back and observe again for a while and see how you've modified the system and try and find, again, one opportunity where you can exploit. You're not trying to fix anything, right? You're not trying to play an infinite game. You're just like in this moment in time, right? And that's just not true in medicine. Getting the right answer doesn't give you anything, right? Predicting something, knowing, like you can't exploit by just prediction. You then need to fix it.
Oh, okay. So the interventional strategy, I see. So you would need to have a causal model that not only makes a prediction, but then also monitors the, oh gosh, that's much harder. Okay.
Right? It's hard, right? Like, so what? You predict this person is going to die. You predict this person is going to get this diagnosis. What
Right.
can you do about that? And a lot of the things that help you get to the prediction, they're not objective facts. They're just a progress through the medical system.
But in some sense, I would say it makes it easier, no? Like, I mean, I guess in some ways it makes it easier, in some ways it's a lot harder. But I think
It makes it easier to do what, though?
Well, so it makes prediction easier, right? Because if you
prediction, yes.
Yeah, so I would, so you don't think that if you could predict with like a high accuracy some outcome in the next 6 months for the patients, that's already like you can do, what you do with it is a separate problem, but there is it's definitely great, right? And that you can't do in the stock market, as you mentioned, because as soon as you predict it, things change and you have to do it all over again.
I actually would argue that the same thing is true in medicine, right? As soon as you start to scale that, right? As soon as we start to predict that this is the situation, now we've altered reality. And so instead of some of the things that we would have caused us to arrive at the prediction, we now change the treatment, and now those things are no longer valid. Right,
I guess it depends on what problem you're trying to predict, right? Like if you predict like calorie consumption leads to like higher calorie means you die faster, that's a scientific fact. So if you know that, you predict that, that's a good thing. It's not going to change just because you predicted it. But if you're predicting something about the medical system, then that's a different story. I mean, I would say, yeah, that's a problem. That's maybe like a not great problem to focus on. But there is some science, some biology behind it, right? So I think if you can predict it, that's not going to change.
Yeah, it's harder to do that than you might think.
Oh no, I totally
right?
I understand.
Like when you look at medical records, what you end up finding is that and it's the same way we process things, right? Instead of focusing on the objective facts, it's easier to focus on something that somebody else has already summarized. And that becomes the progress through the medical system.
No, I totally agree. But I guess I feel like if I was in medicine, I'll be a little bit comforted that there is some like physical, biological ground truth that we are trying to get at. We might never get there, but it exists. Whereas in financial market is whatever people think something is valued, that's the value. Like there's no truth. It's whatever everybody thinks. So trying to predict what everybody thinks at the same time, having your own thoughts that makes it like a loop. Everybody's going around like a some kind of a hamster wheel, never like converging to anything, right?
I think a lot of it comes down to, and we've talked about this so many times, is how do you describe the system, right? What are the objects within the system, and what are the possible actions? And that's almost what, like, the latent space ends up is some reflection of what the paradigm that you're thinking about this is. And if you can't get causality into that, how do you change it?
So the latent space to me is the space of interventions. It's the space of possibilities, that all the different configurations, if you will. And so if you think about treatments, then you could express treatments as a vector in the latent space.
100% the problem, right? Because we're not trying to understand what's actually happening. We're trying to choose between existing treatments or existing diagnoses, right? How do we know when we have the wrong set of actions or possibilities? It's back to that, like, how do we know that we need to jump to a different way of looking at this problem?
Like the content-based addressing concept.
Right? We've talked about this a lot, right? Like when you're stuck in this one finite game and here are your actions.
Yeah.
So if you view medicine as that, like what are the possible treatments, right? And then you sort of have a classifier or something that just says, okay, well, given this is the best I can do, even though I'm dealing with 30%, 32%, you know,
Certainty.
whatever.
Sure.
It's like, okay, I'll pick this one. There isn't really.
So it's not ideal, but I'm just trying to understand. So let's say there's a classifier that picks between 3 types of whatever drugs that you give to someone, and you're saying that maybe one action should be you go do more exercise and that will fix it, whereas it's not even in your action space, right? So that's a very simplified version of what you're saying. Like, I'm sure it can get more complicated.
Yeah.
But so I think that's a valid point. But I think there are probably, I mean, maybe that's left to the doctor's experience to decide whether they should give that. But I guess you're right. But still, if you had to choose between three treatments, let's say we mistakenly have filtered out the better actions, but there's still an answer which of these 3 will work better for a given person, and there's still some value in doing that, no?
Okay, but if the model, okay, bear with me for a second. If the model for how you determine who gets each of the 3 medications, right, is based on their medical record up until now, right? It's the very moment you roll this out as standard of practice, right? This your model to determine which of the 3 medications you get, right? Now that's become standard of practice. And so now all your EHR moving forward, oh, this is what we do in this, right? Think about how that then sort of comes into a feedback loop.
Yeah, I think that's fair. But then you're not comparing just to the history of the person. You're also comparing to the history of all the other people who have the same problem with their data, but still they showed one treatment was better than the others.
I mean, that is fundamentally the problem. And that's constantly changing. You've changed the game now, right? So now you have these people who have, let's just say it really crudely, they now have like these additional drugs flowing through their body, doing different things, right? So do that with multiple different treatments, right? At the same time.
So multiple treatments, let's look at it as such, that's an extra complication. But let's say the 3
That's
treatments.
reality, right? That is
but most people don't take, I guess, multiple drugs. I mean, maybe
they do.
Sick people do, right? Like there's 1% of people are very, very sick.
Sick people take multiple drugs. You look at people who are sick, and it's gone from like people who were sick used to take, 4 or 5 medications. Now they take 17 medications. Like I've seen people on 40 medications. Like, tell me how you can
Yeah, so it's not going to solve that problem. I guess I'm not saying all the problems can be solved, but I'm just saying, so let's say for the sake of argument that you only get one drug, you have to pick between three. I'm just saying that I guess if you pick the third one for people of some whatever history that all look similar and you're wrong, over time you will show that the third treatment was actually worse. Over time you fix it, you switch to the second one, and over time it will converge to which treatment out of the three is best for what group of people. So at least in this simplified case, I agree that there's lots of complication. If they're all taking other things, then so it might become impossible to come up with a good model. But I think in principle, it shouldn't be. It's just
I mean, I think that there is a reason that this is being used and with more success in oncology than any place else. But my patient populations, that's not who they are, right? I'm dealing with old, sick people with chronic illnesses where they are taking multiple interventions. I mean, I think there's use for it when somebody suddenly gets sick and has some rare disease, right? And maybe you can take phenotype and stuff in. But I guess what I'm seeing is that this population of patients that's really, really ill and consume the majority of the healthcare resources, they're taking everything and they have every diagnosis.
So I think the problem is you're dealing with the, I guess, the curse of dimensionality, right? Because if you're taking like 6 different drugs, then you technically in your data set, you need to have all the permutations and then multiply that by thousands of people to get a good statistics. But because you don't have that, so maybe you just don't have the right enough data, right? And maybe you will never have enough data because there's so many different populations. Yeah.
Can I just want to clarify a couple of quick points? Sorry, very, very interesting. So you made an excellent point there where you have many drugs which are essentially affecting the latent space, but you only have one body, right? So you have many, many different essentially agents coming into the system having an effect, and they're competing with each other. And they're essentially colliding because there's only one body. Like if you only have one of these drugs, if you only take one drug, then it will represent the latent space. It will control the output very efficiently, and you'll get a good result. But if you have many drugs, then that's not going to happen, right? If you start introducing all these other medications, you still only have one body. Like this isn't making that body better, and this is making this body better. It's the same body, right? So you have this bottleneck, which is you, and you're trying to shovel this stuff through that bottleneck. But that's hope, right? Because if we could train this, right, if we could take these different regimes independently and somehow work out, come up with some latent representation of, or even some labeled representation of what they're actually doing, we should be able to see that this one and this one are going to fight over this area of the latent space. They're going to, they're going to cancel each other out or over amplify each other or something. But perhaps this kind of ability to characterize them individually and then stack them up together and see where they overlap might be relevant. So what we could do is we could train one of the heads and see what its principal components are, and then we could train the others, and we can say these two drugs in the latent space essentially compete for controlling the same parameter, right? And so these drugs are essentially going to either amplify each other or cancel each other out. Can we essentially mediate between them or switch to a different drug that uses a different mechanism so that they don't collide? I mean, I think there is hope. I wouldn't say there's a lot of hope, but at least there's hope that we could.
No, I think there's hope, and I guess where I see the hope is with like wearable sensors, and where you really are collecting objective information about what is going on in the person's body. I don't see it coming through EHR.
No, I don't agree.
Like, I think if you're doing constant like analysis of whatever, like blood, temperature, heart rate, I think we're getting to the point where sensors are and the data feeds from that combined with knowledge of, okay, what are the treatments, letting go of diagnosis and stuff, right? I think as soon as you start to put that in, you're putting a structure on it that is our creation, it's our narrative, as opposed to what's actually happening. And so I do see opportunity. I think it works well when you are just collecting streams of data from sensors. But as soon as you start to try do it through EHR, I've kind of given up that that's ever going to, you can predict things, right? And from within the medical system, sure, that makes, you know, to be able to predict utilization or hospitalizations or even deaths, right? That's useful, and there's financial gain there from doing that, and maybe you can help people to prepare in some way. But in terms of taking action and changing things and really changing things and learning new stuff, I personally bet upon sensor data rather than EHR data sets.
But if you can predict things, can't you just play around with your input and see how your prediction changes, and then based on
These
that,
are people we're talking about. Standard
a model.
Yeah, but you can do it in a model.
Oh, so tell me again what you wanted to do with the model.
So you say you have a model that can predict, let's say, someone's death, like likely death at some point in the future. But can't you just go into your model, play around with the input and say which one improves your model's prediction of death? Like very naive way of.
Yeah, there's a great one. Age. Tell me how you're going to change that.
Well, no, but there are things presumably in your model that you can control, like age you can't. But...
So, okay, so like, you know, hospitalizations, utilizations, certain medications, right? Those are the things that show up, right? If you try build a model, say with like an ICU data set or something, or like.
So medication, like can't you like lower or like increase the medication dose in your model and see what the prediction is?
I mean, people are taking medications because they're sick, right? And again, there are only so many options. So you're sick, you have some complaint. Well, all right, we'll try this. We'll add this in here. You get to the point where somebody is taking, you know, 15 medications, 16 medications, they still feel terrible. Yeah, like any model can look at it. I can look at it and tell you, like, yeah, this is a sick person. They're taking 40 medications. If I had to make
that's a good point. Yeah, I mean, there's probably a very high correlation between taking cancer drugs and dying. Doesn't mean you should stop taking cancer drugs.
Right.
That's
right. Like there's something else going on that happens well before all of that. But in the same way, it's easy for us to focus on that. It's easy for models to focus on that too.
Yeah. No,
the mortality rate of hospitals is pretty high.
Don't
Say
go
that
to the
again?
hospital and you'll survive.
The mortality rate of hospitals is pretty high.
Don't go to the hospital, you'll get sick.
Yeah.
No, I mean, that's a well-known fact, right? You're trying your absolute best to stop people from going to hospitals and to keep people out of hospitals. It's like nobody wants to go to the hospital. Like, you go to the hospital for multiple reasons. You're sick already, and then you're sick, you're exposed to.
It's conditional versus unconditional outcomes. That's all.
Yeah.
I gotta jump off, guys. I'd like.
No, we're way over time. So thank you,
Yeah,
everyone. It's wonderful. So I will post in the thing Payam's article, and we'll try and cover that next time. Okay.
Okay, sounds great.
See you later.
Bye, everyone.
Bye.
Bye.